Okay, this is the fourth and actually fifth objectives in Unit 3 for AP Calculus BC. I figured out we need to kind of combine these two short assignments. There's a lot of review stuff, but then there's also some new stuff that's happening as well. So anyway, 3.4 is really dealing with area under the curve, and mostly we're doing approximations here with 3.4, but I am going to talk about how it does become the exact area under the curve. And we're talking about Riemann sums, trapezoidal rule, and definite integrals. First time we're actually talking about definite integrals. Okay, so just starting off real quickly with review stuff for you guys. If we're doing approximate area under the curve, and by the way, remember the area is always a positive value. We can do inscribed rectangles. By the way, Riemann sums. Riemann starts with an R. Riemann rectangles. Rectangles, Riemann sums. So, inscribed rectangles, you always use the shortest height in each subinterval. So there's always going to be an approximation because there's always a little bit under the curve that these rectangles don't get. So it's always an under approximation for inscribed rectangles. It's not always the left-hand side. It depends on whether the curve is increasing or decreasing on that interval. Circumscribed rectangles, we always choose the tallest height in each subinterval. In this particular case, it's a increasing curve, so I was choosing the right-hand side for the rectangles, but notice that the rectangles go a little bit above the curve, and so therefore circumscribed rectangles will always give us an over approximation, at least when we're doing a finite number of rectangles. The best approximation for rectangles is using midpoint rectangles, and we always use the midpoint of each subinterval to get the height. Notice that each rectangle goes a little bit above the curve, but then it's also a little bit below the curve as well. But midpoint rectangles pretty much always gives us the best approximation of the actual area. Okay, now we usually try to have equal subintervals. They don't have to be equal subintervals. We are going to explore that some more later on, but for right now we're going to be using equal subintervals. So delta x is the whole interval, so b minus a divided by the number of rectangles, n, and that gives you the delta x. Now probably most of the time you can actually figure out what the delta x is without doing formal calculations. But just in case you need to do a formal calculation, delta x is the b minus the a divided by the number of rectangles. And so if we take the limit as n goes to infinity, so in other words we're going to do an infinite number of rectangles in a finite distance here, effectively the delta x is going to 0, isn't it? Yes. And what that means then is the approximate area is becoming the actual area. And so if we do that, then that's what's happening, okay? And so the Riemann sums, if we actually take the limit as n is going to infinity, and I'm not dotting all my i's and crossing all my t's here, so please do not get all upset with me about this. We could spend 2 days with it, or we could spend as much time as I'm spending with it right now. That's all we have time to do. But basically what it boils down to is we take the limit as the number of rectangles goes to infinity, which means the delta x's are going to 0, and that the infinite Riemann sum becomes the actual area under the curve, and using calculus it's written in the form of a definite integral from a to b. We read it from bottom to top, from a to b of f of x dx. Okay, and it's based off of rectangles. Okay, so I know that was just happening really fast, but maybe you'll need to stop it and write some of that kind of stuff down. Maybe I'll try to capture this somehow so you can post it moving on. Doing some actual examples here. Sketch y equals f of x on the closed interval. Use 4 subintervals to approximate the area by inscribed rectangles and circumscribed rectangles. Okay, we did this stuff last year in Honors Math 3 or in Advanced Math, whichever way you came. But okay, here we go. It doesn't have to be drawn exactly to scale. Don't stress about that. Now you should be able to. Oh, by the way, 4 subintervals. Let's be really formal. So delta x is 3 minus 1 over 4, which is 1/2, because 2 over 4 is 1/2. And you're going, yeah, I already had that figured out, because distance of 2, and you're cutting it into 4 equal parts. Okay, so you need to be able to do a sketch when called upon of either inscribed or circumscribed rectangles. Okay, so now label things accurately. Okay, and so we've got inscribed. Okay, so now we're doing area of rectangle, base times height. The base are all the delta x. Okay, so we've got delta x of 1/2 times the height. Okay, now, wasn't I choosing the left side for the height of each one of these? Yes, I was, because it's an increasing interval there that we're on. So I did f of 1, and I've got 1/2 times f of 1.5, but f of 3/2 plus 1/2 times f of, the next one is f of 2, and then 1/2 times, and then the next one is f of 5/2. Okay, what now? When do I stop? How do I know when to stop? Well, I have 4 of them, and I'm using the left-hand side for each one of these. So 1, 3/2, 2, 5/2, that's all of them. Now, notice that there's a GCF of the delta x. So anytime when the delta x is the same all the way through and you're doing these Riemann sums, the delta x will be a GCF if the delta x's are all equal to each other. And so because of that, I would say if the delta x's are all equal to each other, just bring it out as a GCF out in front, and then you're just saying the f of 1 plus the f of 3/2 plus the f of 2 plus the f of 5/2. Okay, so probably that's just your first step on each one. Okay, so we really have then 1/2 times, okay, so f of 1, that's 1. 3/2 is 9/4, and 2 is 4, and 5/2 is 25/4. Okay. Okay, so this is 1/2 of, okay, so I got 9/4 and 25/4, which is 34/4, 34/4, otherwise known as 17/2. And 1 plus 4 is 5, but let's get them talking the same language, so that's 10/2. So this is 27/2 on the inside times 1/2, which is 27/4. Okay, and so there is the inscribed area. Now, it's always an underestimate. Okay, now if you find yourself without calculator, you're doing it with no calculator and fractions. Think fractions. Now, circumscribed, which we need to be able to sketch, and circumscribed, we're just doing the right side for this one all the way across. And so you can just kind of do that for your sketches on the homework so that you got inscribed and circumscribed there. Okay, so that label, so circumscribed, okay, remember there's going to be a GCF of the 1/2, the delta x. And this time, where's my first height? Well, this time my first height is not at 1, my first height is at 1.5 or 3/2. So f of 3/2, f of 2, f of 5/2, and f of 2. Again, I've got 4 of them, and it's the right-hand side each time. So I have 1/2 times, okay, well, I have 9 fourths plus 4 plus 25 fourths plus, okay, so if I input a 3, and so I get 9. Okay, so again, this is 17 halves, 1/2 of 17 halves plus 13. But 13 would be 26 halves. And so this is, what is that? 36, 43 fourths. Okay, so obviously there's some difference between these two numbers. Remember, inscribed is going to be an under representation and circumscribed is going to be an over representation. A pretty good approximation would be to actually just average those two numbers. That's how you could do it. Okay. Problem number 2 here. So let's say we have this parabola y equals x minus 1 quantity squared, and we're doing the closed interval from 0 to 3. And we're using 3 subinterval with equal bases and inscribed rectangles. Okay, this is part A. So part A, here, part A, let's do it with the color. Okay, let's go ahead and do it. Now, I will say occasionally, let's see, subintervals, 3 subintervals from 0 to, isn't that just 1 unit each? Yes. So, in inscribed, sometimes they will get you to, just to see if you follow directions and you know what you're supposed to do, they will come up with a ridiculous approximation sometimes, just to make sure that you know the rules and that you can follow the rules. So in this particular instance, there's a GCF of the delta x, which is 1. This is inscribed. So GCF of 1, and then I had f of 1 plus f of 1, because inscribed I choose the lowest side each time, and f of 2. And so we have 1 times, well, f of 1 is 0, and f of 1 is 0 again, and f of 2 is 1. So my approximation is 1, which is a very horrible approximation of this area under the curve. Okay. Now, part B, it says use the same 3 subintervals and midpoint rectangles. Okay, so midpoint rectangles, remember that we're going to be doing the midpoint of each subinterval. Now, the subintervals themselves are the same. So midpoints, the area is approximately. So the base is still 1. In this case, my midpoint for the first subinterval from 0 to 1 is going to be 1/2. And my second midpoint is going to be 3/2. And my third midpoint is going to be 2.5 or 5/2. Okay, and this one is actually pretty good. So f of 1/2, f of 3/2, and f of 5/2. So why don't we use midpoint rectangles all the time if it's so much more accurate? Well, it's kind of a pain too. Besides which, we're only doing approximations here for a little bit. We're really getting to the exact ones anyway. So we have 1 times, okay, so f of 1/2. So 1/2 minus 1 squared is 1/4. and then 3 halves, so 3 halves minus 1, that's 1/2 squared is also 1/4. And then 5 halves, 5 halves minus 1 is 3 halves, 3 halves squared is 9/4. And then all of that is times 1, so let's see, 10/4, 11/4. Okay, so 2 and 3/4 as opposed to just 1. So that's a much better approximation for that one. Okay, moving along here. Another very common and good approximation method is the trapezoidal method or trapezoidal rule. Now all the rectangles, you all are supposed to be familiar with all the different types of rectangles. We have inscribed, circumscribed, midpoint. We also have left-hand rectangles, right-hand rectangles, but trapezoidal method or trapezoidal rule. So obviously we're going to be coming up with some trapezoids here, okay? And it is absolutely imperative that every one of you knows the formula for finding the area of a trapezoid, and that you could actually also recognize a trapezoid as well. Now, the formula for area of a trapezoid and I remember it this way. It's average the bases times the height. Okay, now if you want to be a little bit more formal than that, you could say average the bases, so base 1 plus base 2 divided by 2, because that's how you average two things, right? Times the height. Now, if you're looking at this figure over here that I have and you're saying, okay, well, where are the trapezoids? It's like I have all these little figures, and here's delta x, and delta x, and delta x, and delta x, and delta x. I mean, trapezoids, they have a pair of parallel sides, don't they? And you're going, where are the parallel sides? Well, if you give it a 90-degree turn, you'll see the trapezoids, because the parallel sides are actually the vertical sides. And the delta x is actually the height of each one of those trapezoids. Okay, so how do we find the area from A to B? Well, we could do this 5 different times, since there's 5 trapezoids there. So the area of the trapezoid from A to B using trapezoids. Okay, so the first trapezoid, okay, the bases are the y0 and y1. So average the bases, y0 plus y1 over 2 times the height, and the height is delta x, plus the next trapezoid, the bases are y1 and y2, and delta x. And the next one is y sub 2 plus y sub 3 divided by 2 times delta x, plus the next one is y sub 3 plus y sub 4 divided by 2 times delta x, and I'm running out of space, plus y sub 4 plus y sub 5 divided by 2 times delta x. Okay, now what we notice is that there's a GCF of delta x, but there's also a GCF of 1/2. And so the area overall, we've got the GCF of 1/2 and the delta x. Okay, so 1/2 times delta x, and then what's left behind? Well, I've got y sub 0 plus y sub 1, plus another y sub 1 plus y sub 2, plus another y sub 2 plus y sub 3 plus another y sub 3 plus y sub 4. Are you catching on? Plus another y sub 4 plus y sub 5. Okay, now what do you notice? We had repeats of the y sub things except for the first one and the last. Why is there only one y sub 0 and why is there only one y sub 5? Well, there's only one y sub 0 because it's only used in the very first trapezoid to the left. And the y sub 5 is only used in the furthest trapezoid to the right. And all the others are used in two different trapezoids as we're going ahead and calculating. So the trapezoidal rule is 1/2 times the delta x, and then you got y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus, and you do it as many times as you need to. All the ones in the middle get doubled, and then the last one is just a single. So the first and the last one, those are just singles, and all the other ones in the middle are all doubled. Now, because it's a pretty easy rule to memorize, the AP people that write the test, they tend to not use this actual trapezoidal rule anymore. So instead, the emphasis is usually more on individual trapezoids, and they'll actually make the delta x's different. So this is why it's actually so critically important that you actually know your individual trapezoidal area. Okay, but it's nice to see where the formula comes from. Pretty easy to use, and let's apply it here right now. There's a swamp at the edge of town. If the swamp has an average depth of 7 feet, how much fill dirt is needed to fill in the swamp? Okay, we're talking volume then, right? Okay, so if I could find the area of this swamp and multiply it times the average depth, then I would have at least a good approximation of how much fill dirt is needed. Okay, well, what kind of shapes am I getting here? Am I getting rectangles? No, not really rectangle. It's more like trapezoids, isn't it? Okay, let's do the trapezoid method. Okay, so sometimes we go ahead and call it T instead of A. Okay, so there's a GCF of 1/2, and the delta x. Notice all my delta x's are 20. Okay, and then my heights, the first one and the last one are just one time, and all the other ones in the middle are doubled. So 90 plus 2 times 120 plus 2 times 128 plus 2 times 117 plus 2 times 101 plus 2 times 77 plus 2 times 64 plus 2 times 51 plus 2 times, excuse me, not 2 times, but just plus 1 0. So the first and the last one are just one time. Okay, so I went ahead and did it just to make sure that I'm matching up. Now, probably you'd find yourself with a calculator just to crunch numbers for a problem like this. But, it's still important to make sure that you're actually showing the setup anyway. So we have 10 times, and we've got 90 plus 240 plus 256 plus 234 plus 202 plus 154 plus 128 plus 102, and so that's 1406, which is 14,060 square feet. Okay, which means if we multiply times the average depth, fill dirt needed, maybe it might be helpful if I spelled needed correctly. Needed approximately 14,060 times 7 equals 9,842 cubic feet. Okay, so 10,000 cubic feet definitely ought to do it. Okay. Now, we are also doing the 3.5 here. These two assignments are very short, and we need to put them together because I'm looking and we're a little bit behind where we need to be, and everything is so tight as it is. So, properties with definite integrals. Okay, now we've already dealt with some indefinite integrals, and the indefinite integrals, some of those properties are the same. It's just we have more properties when we have definite integrals. So, remember we talked about the fact that the definite integral from a to b of f of x dx is representing area from x equals a to b. Now, it becomes more than just that, but we're going to start with that sort of thing and build from there. And so here's kind of a picture of what's going on. So f of x needs to be continuous and above the x-axis, at least on that interval from a to b. And so that's what we're taking it to be, the fact that the integral from a to b of f of x dx represents area. Okay, so notice if I go from a to b, that's like the length, and then the f of x's are the heights, and we break it up into all those, and we sum it all up, and we get the area under the curve. Okay, well, take a look at the definite integral from a to a of f of x dx. Well, if I'm only going from a to a, my length is 0. So wouldn't it make sense that 0 times the height is 0? Hopefully that makes sense to you. If I go from a to b of f of x dx, a to b, that's a positive. So as I go from left to right, that's a positive length times the height. Then it's going to be equal to, so if I go from the right side to the left side, b to a, and then the height, that actually gives me the negative values. Okay, so from b to a of f of x dx, they're opposite of each other, so I have to multiply by -1. Property number 3 it does work for the indefinite integral. So if you have a constant times f of x, you can bring the constant out in front of the integral. If you have pluses or minuses in between, you can integrate term by term. You can break them apart and integrate term by term. If we have an integral from a to c of f of x dx plus integral of c to b of f of x dx. Now the key is that c is between a and b. Okay, so let me put a c in there so that it's between a and b somewhere. So would it make sense that the integral from a to c of f of x dx plus the integral from c to b of f of x dx would be equal to the integral from a to b of f of x dx? Yeah, I think that makes a lot of sense as long as c is between a and b there. Okay, so those are the properties of the definite integrals, and we're going to do a couple sample problems here right now. So using the properties, and I'm also giving you these definite integrals that these are all true statements about it. And right now I know that some of you might be saying, but wait a minute, getting some negative values there. How are we getting some negative values? Okay, well, the negative values, it does apply even when the curve is not above the x-axis. And so and I forgot to fill this part in, so I'm just filling it in right now. Okay, so the top 3 are dealing with a function f of x, and the bottom 3 are dealing with a function g of x. Okay, so so the definite integral from 2 to 8 of f of x dx. Well, I'm looking here, I see one with a 2, it goes from 2 to 5, and I see one that goes from 5 to 8. So if we're being really, really formal here, I could say this is equal to the definite integral from 2 to 5. Don't forget our dx plus the definite integral from 5 to 8. Which which is then 7 plus -3, which is 4. Okay, and I know some of you guys are going, why do we have to do all that? Well, okay, you got to at least do this last bit right there. Okay, maybe you don't have to do the really formal stuff right there, but at least this last little bit right here. Sometimes we've got to do the really formal stuff just because it's kind of confusing otherwise. Let's see. Definite integral from 5 to 8 of 3 times f of x. Well, this is just 3 times definite integral from 5 to 8 of f of x dx, which we have the 5 to 8, so this is 3 times -3 equals -9. Okay, again, at least this last little bit right here. 8 to 5 of f of x dx, and you're going, oh, come on, Mr. Hobbs. It's, this is the same thing as -5 to 8 of f of x dx, and so that's opposite of whatever 5 to 8 is, which is -3, and so this is +3. Okay, so at least that bit right there. Okay, this one, again, I'm showing you the really formal stuff here. So I could have 4 definite integral from 2 to 8 of f of x dx minus 3 times the definite integral from 2 to 8 of g of x dx. And 2 to 8, didn't we do 2 to 8 earlier? Yeah, 2 to 8 of f of x, that is 4. So 4 times 4 minus 3 times, okay, 2 to 8 of g of x. 2 to 2, well, that was just given to us. 2 to 8 of g of x is 12. So 3 times 12, so I've got 16 minus 36, which is -20. Okay, 5 to 7 of f of x, and let's see, 5 to 7, okay, well, let's see. Five to 7, okay, so I think we've got to use the 5 to 8 and the 7 to 8. Okay, now, the key here is to understand that essentially these can be written up as an equation. And so, since I have 5 to 8, which kind of covers the whole thing, and then the 7 to 8, so the 5 to 7 plus the 7 to 8 is equal to the 5 to 8. Okay, now we want the 5 to 7, so what would we do? Wouldn't we subtract the 7 to 8? Okay, so if we subtract 7 to 8, the 5 to 7 then is 5 to 8 minus the 7 to 8, and the 5 to 8 of f is -3, minus the 7 to 8, which is -2, and so -3 minus a -2, so -1. Okay, sometimes they do get a little bit trickier, and sometimes you got to be a little bit more formal maybe here. Okay, finally, 8 to 3 of g of x dx. Okay, so 8 to 3, well, first off, the 8 to 3, we want to recognize the fact that this is the same thing as opposite of 3 to 8. Okay, and then we'll figure out what that's going to be. Now, the 3 to 8, since we just did one of these, where is that? Here it is. 2 to 8 covers the whole thing. 2 to 3 plus the 3 to 8. So we've got the 2 to 3 plus the 3 to 8 is equal to the 2 to 8, and so the 3 to 8 is equal to the 2 to 8 minus the 2 to 3. Okay, now what is the 2 to 8? The 2 to 8 is 12. And the 2 to 3 is 2, I think. 12 minus 2 is 10. So that's what the 3 to 8 of g of x dx is. And so this is negative 10.